Well, this is crazy. I'm sitting here and I might be watching the laws of physics being broken. This is crazy. I have water here. As you can see by the thermometer, there's the zero mark. The zero mark, you see it? This is about 6 to 7 degrees, 6 degrees below 0 Celsius. And yet, I still have liquid. Now to prove it, I've got another test tube of distilled water right here, and it's frozen. It's frozen solid. So what's the difference between this water and this water? Let's find out. To answer the question, no. The laws of physics weren't being broken just then. Actually, what's going on is something that we call a colligative property. Now, colligative property, the word colligative, that is, means depending on the collection. The collection of what? Well, in this case, we're talking about solute particles, non-volatile solute particles, that is to say, something that doesn't vaporize very easily. Non-volatile solute particles in a solvent will cause certain properties to be changed in that solvent. For water, for instance, I put a little bit of sodium chloride in that water, and in doing so it caused the freezing point of that water to be lower. Now we'll explain why that is in just a moment, but this is one example of a colligative property. Again, depending on the collection of, in this case, solute particles that are found in that solvent. Now, it's important to note that we have two different effects that come from electrolytes and non-electrolytes as far as colligative properties go. Because you can dissolve, say, sodium chloride in water, or you could dissolve sugar in water. Which one would have the greater effect at the same concentration? Well, the electrolyte will, and here's why. Electrolytes, we're talking about things that are normally ionic, right? They can actually conduct electricity through the solvent. Ionic compounds like sodium chloride, when they get into water, they dissociate, don't they? They give us a sodium ion and a chloride ion. For every formula unit of sodium chloride, we get two particles for the price of one. But that's not the case for non-electrolytes, molecular compounds like sucrose, for example, table sugar. So whenever we put table sugar into water, remember we talked about solvation the other day, and there's no dissociation that occurs, is there? For every formula unit of sucrose, we just get that one formula unit. All right, so that's why we see a little bit more of an effect with things like sodium chloride, with these electrolytes that go into water. That's the reason why salt is used in the wintertime whenever we think that there might be some wintry precipitation coming. They'll spray salt water on the roads. And the reason is to help lower any melting point of any precipitation that falls on the ground. Keeps it from actually freezing, hopefully. Okay, so let's go ahead and talk about these colligative properties. And to do that, I'm going to go to the other board. All right, this is to represent something called vapor pressure. Over here we have a beaker filled with just water, just distilled water, if you will. You've got these water molecules throughout the water. Now, in the liquid state, you'll have these molecules actually in the liquid state, of course, but you'll also have, at the surface especially, a few molecules that achieve vapor status. In fact, they'll kind of bounce back and forth. If this is a covered beaker, they'll kind of bounce back and forth in here, and you'll have a whole lot of these little molecules just kind of dancing around in there. Vapor pressure. The more molecules we have banging around and colliding, remember, collisions equal pressure. The more that we have of those, the higher the vapor pressure. But in this one, we've added some sodium chloride. You'll see we've got sodium ions represented in green, chloride ions represented in purple, and you'll notice that you could think of it this way. the water molecules are sort of too busy congregating around the sodium chloride, and they're not really involved very much in going up into the parts above the surface of the water. So we actually lose some vapor pressure when we add the sodium and chloride. Or you could think of it in this way, that the sodium and chloride ions, the ions, are kind of getting in the way of these water molecules trying to get to the surface, and therefore not really able to achieve vapor status. So again, when we add a solute to a solvent like water, we actually see that the vapor pressure is decreased. This is a colligative property. Now we can actually figure out mathematically what the new vapor pressure is going to be. If we want to figure out the final vapor pressure, pressure P, final vapor pressure, we would take the initial vapor pressure, or the one without any kind of solute, and we would multiply it by the mole fraction of water in this case. This is called Raoult's law. Now I'm going to use these diagrams to explain what happens when we add a solute and it changes the boiling point. If these are both open, I've taken the watch glasses off the tops and these are now open. These water molecules are free to escape. And these water molecules are free to escape. The same principle is in effect. Now remember that when you have boiling, what is happening is that normally the atmospheric pressure presses down on the water molecules and keeps them at bay because the atmospheric pressure is stronger than the vapor pressure. But if we increase the kinetic energy enough to where these water molecules have enough kinetic energy so that more of them can become vapor, it gets to the point where the vapor pressure actually equals or is in excess of the atmospheric pressure. And when that happens, we have boiling. So coming back over here, if we put a solute into that solvent such that the water molecules have a harder time of getting to the surface, it stands to reason that they're going to require more kinetic energy. And the more kinetic energy we put into it, that means the higher the boiling point is going to be. So therefore, we call this boiling point elevation. Boiling point elevation. Again, it's what happens when we add a solute to this solvent, and then in doing so, we make it more difficult for molecules of this solvent to escape the surface and to escape when it comes time to boil, when we've had enough kinetic energy to get to that point. Mathematically, to find the boiling point elevation, we use this formula right here. This is the change in boiling point temperature, change temperature of boiling. This is what we call the Van't Hoff factor. It's a factor that we use to tell the number of particles per formula unit. As an example, remember we said that sodium chloride, when it gets into solution, it dissociates. It becomes the sodium ion and the chloride ion. Well, that means we have 2 particles for every formula unit. So the Van't Hoff factor would be 2 in this case. The K sub B is the boiling point elevation constant. This is a number that you would be given. Every type of solvent has a boiling point elevation constant. And this is something you'd be given or you'd have to look up on a table. And finally, lowercase m, that is our molality of the solution. Molality, something that we talked about in section 2. So we're actually using that here in this equation. The boiling point elevation equation. For freezing point, something a little different happens. Now in this case, what we have are the solute particles getting in the way of solvent particles that are attempting to come together, intermolecular forces drawing them together to the point where they will be in a frozen solid state. But if you have solute particles in there, those solute particles may very well get in the way of that happening. So what it requires then is that you have to reduce the kinetic energy lower and lower and lower, even below the point where you had before to achieve a freezing point. You could think of it almost like a third wheel. You ever been in a situation where you wanted to get to know someone a little better, and so you made your way over to that person only to be cut off by someone else that you really didn't want to talk to? That's the solute particle. The solute particle getting in the way of solvent particles coming together and forming that frozen state. Those intermolecular forces being able to take hold, the attractive forces being able to take hold and cause those solvent particles to come together in a solid state. That's sort of like what's happening in the freezing point depression. Now, we have a formula for this as well. It looks just like the boiling point elevation equation, doesn't it? Except just the different subscripts. This is the change in temperature of freezing. This is, of course, the Van Hoff factor. Again, same principle. This is the freezing point depression constant. It's something you'd have to be given or it'd be on a table for you. And yes, finally, molality. Again, the same as we've used with the boiling point elevation. So with a solute in solution, what we see is that it essentially expands the temperature range of the liquid state. The boiling point increases, the freezing point decreases. You see, we get an expansion of that temperature range for the liquid state. Now, I'm just going to briefly mention about osmotic pressure. This dotted line represents a semi-permeable membrane. For those of you that recall the definition of osmosis, we have to have a semi-permeable membrane, don't we, in that definition. And we have mostly water on this side. We have some water and some solute on this side. A few solute particles over here, but really there's more water over here than there is over here. Or we should say it this way, there are more solute particles over here than over here. This would be dilute, this would be more concentrated. So since we have a greater amount of solute over here, the water will attempt to even that concentration out. It's going to pass across this membrane, and in doing so, it's going to increase the amount of pressure, the osmotic pressure. And since the water only comes really one way because there's more concentration of solute particles over here, the water wants to be all even-handed about it, and so it wants to make sure that everyone has the same concentration. It's going to increase the pressure on this side because it's going to flow over here. Osmotic pressure. But we really don't have any problems that we're going to work with that. I just want you to know the concept, or just be familiar with the concept for now. So let's do a couple of quick problems just to give you an example, and we'll use this. What is the freezing point, the new freezing point and the new boiling point of a 0.29 molal solution of sodium chloride? Aqueous solution, which means what? Dissolved in water, right? So we're going to use the constants for water because that's our solvent. The freezing point constant of water is 1.86. This is actually something you'd have to be given or it would be on a table. 1.86 degrees Celsius per molal. And those are just the units that we use. You'll see why in a minute. The boiling point elevation constant of water is 0.51 degrees Celsius per mole. All right? Now, if it's NaCl, what is our Van Hoff factor? Right, 2. Van Hoff factor is 2 because each sodium chloride formula unit gives us a sodium ion and a chloride ion. So 2 particles for every formula unit. So now that we have everything we need, let's solve the equation. We have the change in freezing point temperature here equals the Van Hoff factor times this constant, K sub F, times the molality. Now, important to note, there is no unit involved with Van Hoff. It's a dimensionless factor. So we have 2 times the K sub F, which is 1.86 degrees Celsius per molal. Now the reason why we do that is because molality is right here, isn't it? So we have 0.29 molal, and when we do that, this and this cancel. We're left with degrees Celsius, which is exactly what we want. So when we do the math here, we get 1.1 degrees Celsius. Now, important to remember, this is the change in freezing point temperature. Which way is it going? Down. So our new freezing point is going to be 0 minus 1.1 degrees Celsius or negative 1.1 degrees Celsius. All right, let's do the boiling point now. I'm going to move over here a little bit. Our boiling point elevation, the change in the boiling temperature is equal to, again, Van Hoff times K times the molality. Van Hoff factor is 2. The KB is 0.51. And the molality, again, is 0.29. So we do the math, we get around 0.30, roughly. 0.30 degrees Celsius. Which way is this going? That's right, up. So our new boiling point will be 100 plus 0.30 or 100.30 degrees Celsius as our new boiling point. You get it? You see how to do it? Once you have all the units figured out, you're pretty good to go. Now, what if we tried to find the vapor pressure change in a solution where normally the vapor pressure of water would be 23.8 torr. Let's say though that it's a 3 molal solution. All right, we're going to use Raoult's law. The final pressure, the final vapor pressure is equal to the initial times the mole fraction. So if it's a molality of 3 moles per kilogram, of course we have 3 moles of solute in there. All right, how many moles of water do we have? Well, all we do is we take 1,000 grams in 1 kilogram, 1,000 grams of water, we divide by 18, and we get 55.6 moles of water. And now we can determine our mole fraction of the water. Remember, mole fraction is equal to moles of what you want over the moles of everything. So moles of water divided by moles of solute plus moles of water, and that gives us a mole fraction of 0.95. All that's left is to multiply 23.8, our original or our initial vapor pressure, times 0.95, our mole fraction, and we get 22.6 torr. So that's our new vapor pressure. So look at that. You're all done with chapter 14. Well, what did we learn? Well, remember the first section, we talked about types of heterogeneous mixtures, didn't we? Things like colloids and suspensions. Then in the second section, we talked about different ways of computing concentration, things like molality and molarity, percent by mass, percent by volume, mole fraction. In the third section, we talked about solvation and the factors that we see that affect solvation. And then finally today, we talked about colligative properties. So if you have any questions, go back over the other videos, and if you still need some help, please give me an email. I'll be glad to help you. So I hope it's gone well for you so far. I really do, and I can't wait to see you again. If you need anything, give me an email. But until then, God bless.